Welcome to AP Calculus. In this lesson, we're going to review a few topics and then learn two new ones. First, we're going to review fundamental theorem of calculus, average value of a function, and mean value theorem for integrals. Then what we will do is use the definite integral to define a function, so that's new. And then the second fundamental theorem of calculus will be a new topic for us. Here's our fundamental theorem of calculus. If a function f is continuous on a closed interval a, b, and f is an antiderivative of f, so that's big F represents the antiderivative of little f, on the interval a, b, then we can say that this integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. And we did this in class. We wrote the intermediate steps in this way, where we take the definite integral and first find the antiderivative function. And we said that we no longer need the plus c. Don't need plus c for definite integrals. Because it always cancels. All right, so then the next step of the fundamental theorem of calculus says take the upper bound b, plug it into the antiderivative, then take the lower bound b and plug it into the antiderivative and find the difference of the two. And that's what we have here. We have a few guided examples to work out just to keep this in good practice. So first, let's find the antiderivative function. That gives us a 1/3 x cubed minus 3x. We put the vertical bar as a placeholder for our bounds. Then the fundamental theorem says to plug in the top bound. And I'm just using these brackets to help us see the upper bound and the lower bound. So this is representing our f of b, that first bracket, and this is our f of a. The first bracket has the upper bound 2 plugged into the function. The second bracket has the lower bound 1 plugged into the function. So now we can simplify. 2 cubed is 8, so we have 8/3 minus 6, and then we subtract 1/3 minus 3. This gives us 8/3 minus 6 minus 1/3 plus 3. And we got that by distributing this minus through here. Now we can say we have 8/3 minus 1/3 is 7/3, and -6 plus 3 is -3, but we want to rewrite that 3 in terms of thirds, so let's make that minus 9/3. 7 minus 9 is -2/3. That's our answer. We can check our answer with our calculators. So if we type in math 9, that gives us our definite integral. Our lower bound for this is 1. Our upper bound is 2. Our function is x squared minus 3. And then our integration variable is x. We hit enter. We got -0.6 repeated. Math frac gives us the -2/3 that we got for our answer. Good. I'm just going to clear some of this out so we have room for our next example. So with example B, the first thing we want to do is rewrite this radical using exponents. So example B, we start with a rewrite, the definite integral from 1 to 4 of 3 times x to the half power dx. Then we find the definite integral. So we have 3 times x to the 3/2 divided by 3/2 with our bounds of integration. When we divide by a fraction, it is the same as multiplying by the reciprocal. So we have 2/3 times 3x to the 3/2, 4 to 1. We see that our 3's will cancel. So we have 2x to the 3/2 on the interval 1 to 4. And we plug in the top bound first. 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. When we have a fraction exponent, the bottom is the root. So the 2 root is the square root. The square root of 4 is 2. And then the top part of the fraction is our exponent. So we want to take the square root of 4 and cube it. So that gives us 2 times 8. And 1 to any power is 1. So that's 2 times 1. We get 16 minus 2. We get an answer of 14 here. And again, if you wanted to check that you did this correctly, you can go to your calculator. Math 9 is the integral from 1 to 4 of 3 times the square root of x. And our integration variable is x. And we see we got 14 matches our answer. Great. And we have one last example here. So we should recall that secant squared x is one of our memorized antiderivatives. We should ask ourselves, what function has the derivative secant squared? And hopefully you say tangent of x. So that means our antiderivative is tan x with the bounds from 0 to pi over 4. Fundamental theorem of calculus says plug in the top bound first, then subtract when you plug in the bottom bound. Tangent of pi over 4 is 1, minus tangent of 0, which is 0. We get an answer of 1. Moving on to our next topic, average value of a function states if f is integrable on a closed interval ab, then the average value of f on this interval will be 1 over b minus a times the integral from a to b of f of x dx. If we look at an example, let's say f of x equals x squared on the interval 1 to 4. We can say the average value is 1 over 4 minus 1 times the definite integral from 1 to 4 of x squared dx. This gives us 1/3. The antiderivative is 1/3 x cubed, and then the bounds of integration. I'm going to multiply these 1/3s together. That gives me a 1/9. And then we'll do 4 cubed minus 4 to the first. This gives us 1/9 times 64. Oh, silly me, that should have been a 1 to the third here. 64 minus 1. This gives us 1/9 times 63, and our answer is 7. And that is the average value of f of x on the interval 1, 4. The next topic is the mean value theorem for integrals. If f is continuous on a closed interval ab, then there exists a number c in the closed interval ab such that the definite integral from a to b of f of x dx is equal to f of c times the quantity b minus a. You should see that this looks familiar to what we just did on the last slide. If I divide both sides of the equation by b minus a, you see that they cancel here, and that gives us 1 over b minus a times the integral from a to b f of x dx is equal to f of c. And we can put this into words. We can say that there's a value c such that if we plug it into f, it will be equal to the average of f. There exists a c such that f of c equals the average value of f of x on the interval ab. And that's true because this is a continuous function. So we have all those intermediate values that apply. Here's our guided example. At first, they want us to find an average value of f of x, and then after we find the average value, find the value c that makes the function equal to its value, its average value. So let's start with the average. Equal to 1 over 4 minus 1, the integral from 1 to 4 of 3x squared minus 2x dx. We can say that the average is equal to 1/3 times the antiderivative is going to be x cubed minus x squared, and the bounds of integration are 1 to 4. The average value is 1/3, and in here we have 4 to the third minus 4 squared. And then we're going to subtract 1/3, 1 to the third minus 1 squared. And this gives us 1/3. So 64 minus 16 is 48, minus 1/3. 1 cubed minus 1 squared is 0. So that's 0 times anything is 0. And now we can say that 1/3 of 48 is 16. That is equal to our average value of the function on the interval 1, 4. So I'm going to write that up here. Average is equal to 16. I'm going to clear out this work so that we can do the next step, and that is the mean value theorem part of finding the c value, where the function is equal to its average. All right, so to find the c value, we take the function 3x squared minus 2x, and we set it equal to its average and solve for x. This is a quadratic function. Let's get 0 on one side. Now we would like to factor this. Let's see, 3 times negative 16 is negative 48. And we need two numbers that multiply to negative 48 and add up to negative 2. So we have 3x squared minus 8x plus 6x minus 16 equals 0. Factor by GCF. X times 3x minus 8. 2 times 3x minus 8 equals 0. We get x plus 2 times 3x minus 8 equal to 0. X plus 2 equal to 0 tells us x equals negative 2. And 3x minus 8 equal to 0 tells us x is equal to 8/3. We have two answers here, but now we have to go back and say, do these answers exist in the interval 1, 4? We see that negative 2 does not. 8/3 is 2 2/3. That does exist in that interval. So c is equal to 8/3. That is the value predicted by the mean value theorem. Next, we look at using the definite integral to define a function. We see that we've been working with the definite integral where we have constants in the bounds of integration from a to b. But now we're going to be looking at the definite integral when we have a variable in the function. So from a to x instead of from a to b. And what this says is f of x equal to the antiderivative from a to x, f of t dt, means that f of x is equal to f of x plus f of a. So f is the antiderivative function, capital F is the antiderivative function of lowercase f, and then we have to plug in our bounds of integration. So let's look at this with an example. f of x is equal to the antiderivative of cosine of t, which is sine of t. My bounds of integration go from 0 to x. F of x is equal to sine, we replace t with x, that's the upper bound. Then sine, we replace t with 0, that's the lower bound. F of x is equal to sine of x, because sine of 0 is 0. And that is our function defined by the definite integral. Now they give us a second part where they say, evaluate this function for the different x values here. So if I evaluate f of 0, I simply have to plug 0 into sine, I get 0. If I evaluate f of pi over 6, that's our next one. Sine of pi over 6 is 1/2. Next we have pi over 4, we plug that into the sine. F of pi over 4 is root 2 over 2. Then we have f of pi over 3. That gives us root 3 over 2. Oh, my marker went out. And finally, f of pi over 2 is sine of pi over 2, which is 1. All right, so we can just put in a blank slide here to do another example. F of x is equal to 1 to x of t squared dt. F of x is equal to, what is the antiderivative of t squared? Well, that is 1/3 t cubed with the bound from 1 to x. Again, we don't need to plus c because we're dealing with a definite integral, because we have values on the bounds of integration. Now, the fundamental theorem of calculus tells us to plug in the top bound. So we have 1/3 x cubed minus, let's plug in the bottom bound, 1/3. And this would be our function defined by the definite integral. And if we wanted to, we can evaluate this for some different values. So let's evaluate it for 2. That would give us, plug in a 2 for the x. That would give us 8/3 minus 1/3, which is 7/3. If we want, we can evaluate it for, let's say, 3. That gives us 3 cubed is 27 over 3 minus 1/3. That gives us 26/3. So we saw a trig example, and now we saw a polynomial example. This is useful if we're evaluating the definite integral for many different top bounds. Instead of solving the definite integral each of those times, we can solve it once as a function and then plug in all of the different top bounds to get the answers. But using this is also helpful in our next topic, which is the second fundamental theorem of calculus. And the second fundamental theorem of calculus, again, has a variable in the bounds of integration, but at the same time, we are evaluating the derivative of the integral with the variable in the bounds. So let's look at a simple example with this. If I were to take f of x equal to 1 to x of t dt, we can say that f of x is equal to 1/2 t squared from x to 1, and then f of x is equal to 1/2 x squared, that's the top bound, minus the bottom bound is 1/2. Now this is what f of x is, but recall the second fundamental theorem wants us to take the derivative of this. So we can now say that f prime of x is equal to the derivative d dx of f of x. Well, we just found that f of x was equal to all of this. So f prime of x is equal to the derivative of 1/2 x squared minus 1/2. And the derivative of 1/2 x squared is 2x. Well, it's just x. 2 times 1/2 is going to cancel, so it's x. And the derivative constant is 0, so we get just x. That means we could have saved ourselves all of this work and said just replace this with x. If we're taking the derivative of the integral, then we get just x. And we can write this question a little bit differently. F prime of x is equal to the derivative of the integral from 1 to x of t dt. And we can say since we're taking the derivative and the integral, they're going to cancel. So the function stays the same, except we're replacing it with this variable, and we get just x. And I didn't have to do all of that work. We're done. The only time that it becomes a little bit more complicated is when the variable part of the function that we're plugging in is a little more complicated. Right now, if we look at this, we can say that the derivative of x is 1, so it's as simple as plugging it in. But what happens when the derivative of that is not 1? And I have an example here for us to look at. Now we see we're plugging in x cubed. Well, what's the derivative of x cubed? 3x squared. So this is going to affect our answer. It's not going to be a simple plug-in. If I'm looking for f prime of x equal to the derivative of the integral from pi over 2 to x cubed of cosine of t dt, I just can't plug in that x cubed and be done with it because this function's derivative is not 1. So let's explain this in a way that we can systematically apply it. We're going to let t be equal to our function in the integral x cubed. Well, if t is x cubed, then dt is the derivative of t would be 3x squared. That means I should replace this with 3x squared and multiply it by cosine, replace that t with x cubed. So f prime of x equals d dx, the integral from pi over 2 x cubed cosine of t dt becomes cosine of x cubed times 3x squared. But it's usually common practice to put the 3x squared out in front. So I'm going to rewrite it that way. 3x squared times cosine of x cubed would be our answer for f prime of x. And that's the second fundamental theorem of calculus. Now, I solved this with the shortcut. I'm just going to add a slide in here so we can solve this the long way. So our integral is from pi over 2 to x cubed. And it's cosine of t dt. That's our f of x. F prime of x is the derivative of the definite integral. So let's first solve the definite integral. The definite integral says that the antiderivative of cosine of t is sine of t. So we have sine of t that we're going to evaluate from x cubed to pi over 2. When we plug in the top bound, we get sine of x cubed. And when we plug pi over 2 in, we get sine of pi over 2 is 1. And we can say that all of this replaces what you see here. Now, to find f prime of x, I need to take the derivative of sine of x cubed minus 1. And you should see that we need to use the chain rule. We have an inside and an outside function here. So what's the derivative of the outside function? Well, the outside function is cosine. We keep the inside function unchanged, but now the chain rule says multiply by the derivative of what's inside, that's 3x squared. And then what's the derivative of a constant? 0. So we like to put this in front, 3x squared times cosine of x cubed. Well, that's the same answer I got with my shortcut, the second fundamental theorem of calculus, which says plug that in for t. We get the cosine of x cubed. But if you're letting t be x cubed, then dt is going to be the derivative of x cubed, which is 3x squared. That square looks like a cube. Let's fix that. And we say, instead of doing all of this work that we did here, the second fundamental theorem of calculus gives us a shortcut. We didn't have to do any of that work. Just plug in the function, and you say, well, if I'm letting t be x cubed, the derivative of x cubed is 3x squared, so dt has to be replaced with 3x squared. And that's it. So you have the lesson here, watch it, pause it, rewatch it, take notes, and then you have an assignment online. I'll email everything to you and post it on our haiku page. All right. Email me if you have questions. If you need a live session of tutoring, we can do that. Just get in touch with me and we'll schedule it.